He has found one simple solution. More than one box hates him. Bug fighters! Hello, I'm Mateusz. I mentioned in the previous video that I need to refactor Yazboot. That led me to think again about strengthening the C++ code. How can I make C++ safer and better with minimal effort spent, usage of correct compiler flags, static analyzers, sanitizers, all tools that can help spot problems in the very early stages of programming, basically in the compile time. Oh, except of sanitizers, they are working in the runtime. Interested? Prepare your favorite drink and let's get started. Before starting my summary of hardening software, let me point out why do I want to do that at all. It seems that this is a hard time for C and C++ languages. There are many reports that show that a huge number of vulnerabilities come from memory management. That's incredibly important for software produced for critical domains. Let's imagine that some nasty hackers black out for hours or even days your neighborhood, breaking into power plants, because some sleepy developer hasn't caught buffer overflow inside his code. And that's just a tip of the iceberg. If you are a C++ developer, you probably know more issues that you can introduce into your software. So also governments, especially looking at the current geopolitical situations, spot that problem. The United States Office of the National Cyber Director released a report urging developers to transition from memory unsafe languages to more secure ones. C++ was not listed as a safe language. The story is same for huge globally existing corporations. Then you may say, right, but I'm not developing any critical infrastructure, so why should I care? There are many arguments to harden code security and quality. If your software has users, I'm pretty sure that you want to make it stable and secure, especially if you have some data inside it, like some users' private data. Who wants to use software that randomly crashing or leaking their personal data after all? And it's worth remembering, and this is my confession, I sometimes forgot about that. Faster and preferably automatic catching of issues in your code will result in fewer and shorter debugging sessions. You may even save time in some cases. It seems it is a difficult time for C++ standardization committee, but it is their and our developers' responsibility to adapt to the changing world. But it's a complex task, not to reproduce Python's path of migration from Python 2 to 3. So I thought maybe it's time to switch to another, safer language with nice, shiny new features, instead of those old backwards compatibility garbage landfills. Rust is the best fit for my projects aside from C++. However, it has a significant drawback. Rust uses LLVM as its backend, which is the same backend used by Clang by C++. Currently, LLVM doesn't support code relocations using position-independent code, using PIC register, at least for Cortex M0 processors that I'm using. While it has some capabilities for dynamic loading, I need more than this. I could potentially use Rust to create parts of the operating system, but some parts still needs to be written in C++, C, or even in the assembly, at least until the GCC backend for Rust is not ready, or LLVM implements FDPIC relocation support. So could Rust improve quality and safety of my code? After my research, I think that yes, it is. It has totally redesigned some major pillars of the language, which makes it unable to use them wrongly. However, cost effectiveness depends on the particular project. Questions that I personally answered to myself were: does Rust fit into the project? If it's not a newly started project, how long will porting take? Do I want to learn a new language? Are all external libraries that I need in the Rust ecosystem available? And to be honest, those are just tools after all. They are as good as their users. Look what people can do with just Microsoft Paint. Of course, better tools could result in better outputs and significantly improve quality, but in most cases they are not blockers. Then I found projects that were created to extend C++. Two of them, NIM and CppFront, are transpilers. What the heck is transpiler? It's a type of compiler that translates source files from one language into source files of different language, instead of producing machine or virtual binary code. Strostrap brought C++ to life in that way. Important questions. Can NIM or CppFront improve my C++ code? Yes. Their purpose is to break with backward compatibility and fix legacy technical debt. Is it costly? Yeah, could be. But the cost can be divided into really tiny steps, since they produce raw C++ source code. New and old code can be intermixed using exactly the same toolchain. Is this production ready? Most probably not. These are just experiments. They may be abandoned after some time, but it shouldn't be hard to revert to pure C++ after all. Don't forget that you have C++ source code for all the time. Is it hard to inject CppFront inside the existing project? Wear safety glasses, a highly experimental code is going to arrive soon. Time spent on this integration could be wasted. Remember that nothing ventured, nothing gained. I enjoy learning new things and gaining experience, so this will be a good use of time regardless of the outcome. If you need to become more familiar with it, CppFront is a new language built on top of C++. It was designed to demonstrate that C++ can be improved by breaking with the syntax and backwards compatibility. The language creator gave an excellent presentation outlining the advantages of CppFront over C++. Since CppFront compiles its new syntax to regular C++ code, it can be used with even obscure C++ compilers for microcontrollers. However, it's important to note that it was not designed for embedded systems and uses the whole regular standard library with its own dynamic memory allocations. This introduces the risk that the software may not behave in fully controlled way. Dynamic allocation is often unwanted or even wholly forbidden in the embedded world. This issue might hinder the experiment, but that's a problem for future SPI. I've started integrating CppFront with CMake. I found a GitHub repository with a clever idea that allows Cpp2 and h2 files to be filtered out from targets, and I implemented a similar solution. This makes it almost invisible to the user that the CppFront transpiler is being used. But instead of using magic to register files automatically, I used a macro to enable CppFront for the target directly. There were two reasons behind this decision. I can pass CppFront flags for a single target, so that I can modify CppFront flags per target, for example to use pure CPP2 syntax. And pure CPP2 syntax requires h2 files instead of header files, which makes it a little bit harder to interwork with C++. To resolve that, I added C++ modules to my environment. Modules can be imported using pure CPP2 syntax, but modules for C++ require additional property set in CMake. So I have to say the CppFront conversion function that some files contain modules, and that's the second reason. I quickly realized that the solution was not working as intended. The compilation was failing, and there were two reasons. Firstly, some code that seemed fine for regular compilers was not compiling on ARM non-IAB toolchain. Recently I found that it is failing also on regular GCC. So it was also an issue with incompatibility between fNoExceptions flag and fNoRTTI. Secondly, there were a bug in CppFront. When both flags noRTTI and noExceptions were used, RTTI was actually still being in use. To address this, I forked the repository and fixed the bug using a
hacky compile time solution.
I appreciated the concrete error message instead of encountering an unknown exception. And I created my first pull request, including a disclaimer that I was raising an issue and provided not fully clean solution. To my surprise, Herb merged my pull request into the codebase. Yeah, it's my first contribution. I'm really happy about that. I still need to keep my fork, as module support inside CPP front is not yet integrated. However, I have confirmed that the pull request that was created by some author can be manually applied and it works perfectly for me. So lesson for me and others? Do you know that something doesn't work? Raise an issue. Do you know how to fix that? Let's create a pull request. Hopefully it will be merged, but if not, someone may use it anyway, as I'm using module support in CPP front. When I started using CPP2 files, Vim did not support CPP2 syntax. There were no syntax highlighting, no automatic code commenting shortcuts, no license header insertions. It made me feel like I had been transported back to the Stone Age. So I found Vim Polyglot, a plugin that provides syntax highlighting and allows easy addition of support for new languages. So I spent some time, I don't know, maybe 1 or 2 days, adding fancy colors. As simple as possible was to inherit C++ syntax and extend it with a few CPP2 keywords. It's not production ready for anyone, but it's much better than nothing. I also fork Vim Copyright, which generates headers for any open source licenses. And I've added support for CPP2 files. So is it worth to use it in your project? To be honest, I don't know. It depends on many aspects, and the crucial one is that this is in an experimental state. I wouldn't decide to use it for any commercial project, but it has the potential to grow in the future. So if you like to learn new things, it's worth giving it a try for your hobby project. As I mentioned, to use pure CPP2 syntax, only imports are allowed. So, to add interworking between C++ and CPP2, I decided to introduce modules to my project. But that's not the only reason to do that. Modules can also significantly improve code quality and safety. Due to stricter encapsulation, it's easier to create stable APIs that hide implementation details. Life is simpler. Conceptions like pimp pattern or forwarding declarations are no longer a regular part of our coding life. Traditional headers have problems with dependency propagations. It is possible to provide two different declarations of exactly the same symbol. For example, you declared a class in one file and class in another file with change destructor. Modules also significantly reduce problems with one definition rule. It's much harder to break it. They also provide new compile checks to validate ABI compatibility between interworking translation units. And thanks to that, I have already found issues with incompatible flags used in my Yazboot project. Such issues generate hard to debug runtime issues, where magic happens, like thumb code accidentally changing to an arm in some function, or hardware register that was never correctly initialized is used to jump to some random address in the memory space. You saw them in my previous videos. And of course I faced a problem. Modules use a build system to scan dependency trees. CMake already supports that, using the Ninja build system. However, dependency scanning for modules also requires GCC in version at least 14. Which unfortunately was not yet released when I started working on it. So I compiled my own GCC 14 for ARM, then a new YASLD toolchain also with GCC 14, and I encountered a lot of internal compiler errors. But I still haven't given up and started digging inside GCC Bookzilla. Fortunately, I found a reported issue that I faced, so I applied some already proposed patches to my GCC, making the modules usable. Someone might criticize, but almost no compiler delivers modularized libstd. And that's true. However, in module files, it's still possible to include legacy includes. Finalizing modules will definitely solve some issues with the C++ language. Of course, they do not address all of them, but at least some. The introduction of modules would also be divided into steps, and the needed effort is not high. You just need to remove header files, mark exported interfaces into source files, and replace includes with imports. However, today's modules are not yet ready to be used except for, again, hobby projects. Time spent on debugging ICEs might be too huge to justify the usage of modules, and it may be too hard for casual language users. Also, you could land in place that you are not able to fix problem because of bug in the compiler. In my opinion, one of the C++ big disadvantages is that it does not use correct default values and behaviors. I think that the compiler should be as strict as possible by default, with all warning checks enabled. Then, if something is not suitable for your project, it is better to disable it than not know that some tools even exist. Safe by default, unsafe on demand. The same goes for default variable scopes and constants. Class members are private by default, but variables should also be const by default, parameters should not be mutable. It's better to relax rules or checks when compilation phase than to think about every line of code constantly. I also made the same mistake with flags propagation in CMake. I utilized target dependency propagation. Let's consider a simple example. We have libraries A, B, C, and D. A inherits B, B inherits C, D inherits C, and is inherited by A. I forgot to link the flags target in D, and I encountered serious problems several times because of this, like ARM code generation instead of TAM. That problem is now verified by the compiler when using modules. However, that issue impacts more aspects of software architecture. This is just one example of that. So I started placing all flags, warning, errors checks in the global compiler and linker variables in CMake. Global variables are bad in most cases, I can agree with that. But when dealing with flags, particularly in the embedded world, where only one target is built at the end, containing everything, the whole operating system, libraries, and firmware inside it. Basically the whole ecosystem. It's already a global environment, therefore flags should be also global for each piece of that ecosystem. Enabling flags is almost costless, but manipulating the flag set will likely cause failures in some areas of your already existing code, requiring some time to fix. However, it's likely to be worthwhile. Correct defaults are hard to misuse unknowingly, and this is also a valid comment for regular code. Think about your defaults, default behavioral functions, default initializations. You have good defaults, your code most probably won't be misused in any case. I don't understand why the compiler safety checks are not enabled by default. At least I don't know any compilers that do it. Utilize available flags designed to help you spotting potential problems as soon as possible. They were created to do that, not to distract us. Static analyzers, runtime, but compile time, bug detectors. I already knew tools like cpplean, sonarcube, cppcheck. The problem with that tools I always had was they were bloated with false positives, which always makes me crazy and finally forces me to turn them down. On the other hand, clunktidy was a better solution. By partially executing precompile code, so it's a runtime execution, but during compile time, real broken flows inside the code were spotted. However, working with the GCC toolchain may interfere with clank compilation, and successful clank compilation is necessary for clunktidy. Recently, I discovered that GCC also introduced its static analyzer. You can enable it via fanalyzer flag. Although the GCC website contains information that C++ is not yet supported, I was able to use it successfully with my simple C++ code. And it spotted a serious bug in my YASLD implementation, where one of the paths led to a null pointer dereference. The beauty of that solution is that it doesn't require any additional steps, except placing the flag in your compiler flag list. It is used during regular compilation, just increasing the number of checks. While this may increase build time, it can be beneficial in identifying potential issues in your project. Null pointer dereferences, memory leaks, usage of uninitialized values, undefined behaviors. Additionally, the analyzer generates graphs illustrating incorrect usages. and paths that needs to be followed to reproduce the issue. Feel free to at least try using this new feature. Since it is a fresh tool inside GCC, it may generate false positives, it may generate internal compiler errors, but if it works for your project, you have 3 additional safety and quality hardening. We can expect that the number of checks and quality of the tool itself will improve in the further releases. If your project uses Clang, try Clang Tidy. It's a little harder to configure since you must select checks for it, but since it can spot bugs, I think it's worth it. Sanitizers like address sanitizer, undefined behavior sanitizer, leak sanitizer, threat sanitizer are helpful tools but imperfect, at least for me. First, it is crucial to ensure good code coverage in your test. Those sanitizers are used in the runtime, and additionally most microcontroller compilers do not support them, because they are using specific library injects in the runtime, replacing some, for example, mallocs to their own provided mallocs. In my case, I would need to increase test coverage on the host machine instead of testing them in the Renode simulated environment. And I prefer testing in Renode simulated environment because I'm testing the real binary that then I'm using on the real hardware. But generally, those could also improve code by finding hidden bugs, but the effort may be too huge for some projects. For me, this cost is too high. I have a hardware abstraction layer, however I cannot keep working on hardware abstraction on the host machine 100% of the time. If your project is executed inside a real operating system and you have good code coverage, you can use them. They are almost free, but you have to execute them inside your continuous integration during running your tests. And speaking about tests, tests are the most critical tool for improving quality, safety, stability, security. It is essential to have multiple levels of testing, but you need to find a balance between time required to create them and maintain. I prefer using tests that primarily verify business logic. So tests that utilize simulated environments are suitable for the embedded world. I write tests to verify real use scenarios, such as YASBoot booting a standalone relocatable executable. Therefore, my code must pass through the entire success path, providing verification for new features and checking for regressions. If you introduce a bug, the test should fail. Although costly, tests provide the best quality checks. Embedded developers often face the challenge of working with devices with minimal resources. However, there are tools available that can help identify areas for improvement. For example, some embedded IDEs, like Code Composer Studio from Texas Instruments, come with embedded profilers. Alternatively, tools like Bloaty can be used without IDE to profile memory usage including RAM and flash. I have also used Bloaty occasionally to optimize memory usage for YASLD and YASBoot. And thanks to that, I reduced memory footprint. I realized that huge amount of memory footprint in both flash and RAM was caused due to runtime checks in CPP front, so for bootloader I disabled them, but for the software, most probably I will use them. They are checking if you are doing null pointer dereference or you are accessing out of the bound. Also in my current job, I regularly use them to add more features without changing the hardware. But remember the sentence: premature optimization is the root of all evil. Did you know that ISO C++ prepared valuable documents on improving code in almost all its aspects? There is a website driven by C++ author Brian Stroustrup and previously mentioned author of CPP Front, Herb Sutter, with guides on how to use modern C++. You can find many topics covered there. If for some reason you didn't know such guidelines are available, I encourage you to check them out. Thanks for watching and let me know your thoughts about improving C++ code quality. If I helped you somehow, you can return the favor by liking or sharing. And don't forget to share your opinions in the comment section.